Okay. So, last class we mentioned about the motion of the meta center. We called it the M curve, how the meta center moves along with the healing. Now, there are note that in general we assume one thing in case of all this healing, that is, we assume that the displacement del is always remaining constant. This is an assumption that we make in the development of all our mathematics theories. The meaning of del remaining constant is that when it tilts like this, whatever is going in is equal to whatever is coming out. Now, when can this be violated? Let us take a look at a case when this concept can be violated. It will happen if, suppose the ship is like this, the half breadth is like, the full breadth is like this, then now this is known as the deck, that is the region at the top, okay, that is known as the deck. Now, suppose the initially the water line is like this, and now suppose the ship heels like this much. Now, it has healed so much that the deck has actually immersed. It is actually called it is a case of deck edge immersion, or the deck edge, not the whole deck of course, the deck edge is immersed. So, this is the deck edge, this region is now immersed in the water. Now, in this case we will see that the volume that has submerged is this, and the volume that has emerged is this. Okay. Now, you will see that a little bit of volume here has been left. I will put it in the opposite direction, right. A little bit of volume has been lost there. If the deck was up to this, then it is okay, we have no problem, but since the deck ended before that, you have a slight problem, that is, this much volume is lost. There is a difference in volume between the side immersed and the side immersed and the side emerged. Okay. This is the side immersed and this is the side emerged. More has emerged, more volume has emerged, whereas less volume has gone in, because this volume is actually air, or when it goes in it becomes water. So, this is not the ship. So, that much volume is lost. So, what do we have? We have the volume immersed not equal to the volume submerged. Now, this is what happens in actual practice. It can happen in actual practice in some geometries of the hull, some types of hull where you have the depth is not too much. When the depth is not too much, such a thing can happen. Now, there are different ways of approaching such a problem. You have to obviously see some method of doing it, that is, in general the problem is more complicated, but we try to reduce it to a simpler case by making some assumptions. Now, how can we make the volumes equal, means the volume submerged and the volume emerged equal. Now, this can be done if, now suppose I assume that it is healing about this, not this point, but it is healing about some point here, then it becomes like this. Okay. Now, what has happened? We had this volume greater than this volume, because of this, this volume is now reduced a bit, it is only this much is, I mean I cannot darken, okay. This volume is out, okay, this volume is not emerged now, whereas there is there is a decrease in volume here. Now, this decrease in volume will imply, and here see this intersection of this line and this line is here now. Therefore, this volume actually starts from here, okay, it opens out like, means it opens out like this from that point. Therefore, we have an increase in volume on this side and a decrease in volume on this side, and we can keep moving that point such that we will have volumes emerged and volume submerged equal. Now, this is the mathematical method we use to make sure that the volume emerged is equal to volume submerged, and so that the mathematics does not get too complicated. But in real practice it does not have to be like that. The ship might heal about any point, and therefore, the problem is a little more difficult. Later when we come to the end of the course, later we will specifically address this problem. Right now I am just mentioning the problem as such and the method of solution, but we will do this in later in the last part of the course. Okay. Now we have mentioned, I have already mentioned to you what we call as the statical stability curve or the curve of statical stability. So, this goes up, comes down like this. Okay. This time it is at 80 degrees in this figure, and I have already told you that at an angle of 1 radians, and you should know also that 1 radian is equal to 57.3 degrees, 57.3 degrees, conversion from radians to degrees. So, at around 57 degrees, 57.3 degrees, if you draw a line, a vertical, and at that point somewhere here, and here if I draw a tangent, if the point at which they intersect is this height will be equal to g m. Okay, this much we derived in the last class. So, this is alpha, and we showed one method of showing that this vertical equals g m, and it is the vertical at an angle of 57.3 degrees, which is equal to 1 radian. No, 57, yeah, this is 1 radian, I think. This is, okay. Then there is a slightly easier and similar way, a simpler way of deriving. Last time we did using a differential form, we differentiated by parts and we got a value that this vertical value was equal to g m. Now we can use another method. Now suppose we have this figure. Now let us take any angle. Okay, this time I will call it phi. Let us suppose we have any angle phi, and I draw a vertical at, means I draw a vertical at some point where this angle, I will not mention, sorry, this is phi. Remember, this statical stability curve is a graph between phi, the heel angle, and gz. Okay, this is the statical stability curve. It is a curve between the heel angle phi and the gz. Now at any phi, it does not matter, some we are to get a expression we are doing at any phi, I draw a vertical. So this height, these things I mention as A, I mark as A, B and C, D, E. So now you can see that directly, we can see that the triangle ABC and the triangle ADE are similar. That you can directly see in the figure. It is the same angles, it's made from the same, all three angles are same. So, it is the similar triangles. Therefore, DE divided by AE equals BC divided by AC. Now I think, okay, I will keep this figure as well. Okay, now we have this. Therefore, DE divided by what is AE? AE is 57.3 degrees, or it is equal to 1 radian, equals BC divided by BC is GZ at that particular value of theta. Is it clear? BC is the vertical distance always represents GZ, because that coordinate is GZ. So, this is GZ and this is phi. So, at any value, this represents the value of GZ at this value of phi. Okay, this is the value of phi. So, phi is changing from 0 to 57.3 to 80, phi is changing like this, and consequently GZ is changing from 0 to whatever is the value at, okay, each thing is changing. Now therefore, at the value of phi you have value GZ, therefore the BC represents GZ at the value of phi divided by AC, AC is phi, let us call it in radians. Okay. Yeah.
So is that B is not on the curve?
B is on the line.
B is on the line. Then how? Why will it represent GZ at the phi?
BC, why should it represent GZ, right?
Yeah.
Oh, actually, okay, that's why it's a good question. The reason is, according to the figure what they have written here, is that BC is, this is the beginning. Okay, so this derivation is actually true when the separation between this curve and the line is not very much. Okay, that's their explanation. So BC is almost equal to GZ. So it's not equal, that's correct, it's not equal to GZ. It BC, if it is on the line, it will be equal to slightly different than GZ. So this is their assumption. So this is equal to GZ by phi. Now that's what this, in a way it's not really correct, but it says that phi is small, and then in the next we are actually going from phi equal to 0 to in fact 57.3, we are extending it. There is a problem in this, but this is what this book does. So phi is small, then therefore DE divided by A is 1 radian is equal to GZ. I write it as GM sin phi divided by phi. Again the concept comes, phi is small. Okay, if you assume that phi is small, then sin phi is equal to phi. Therefore sin phi and phi you can cancel out. Therefore DE becomes equal to GM. All right, you see this derivation. This derivation is not very convincing actually, from the fact that you are assuming first phi to be small, then phi to be large, means in the case when you are extending to the region GM, it is actually phi equal to 57.3. There you really cannot assume phi is small and that sin phi is equal to phi. That derivation has a problem, but if you remember the previous derivation, that is actually correct. So it is just differential. That was a correct derivation, so it's okay. This is a simpler way of deriving it, but you will get the expression that GM is DE is equal to GM. That is, we are getting that DE is equal to GM. So this is that derivation. Therefore what we are saying is that at a point of 57.3 degrees, if we draw a vertical and and if you take a distance GM, you measure a distance GM there, from GM if you draw a line connecting to the origin, you will get the tangent to the curve at that origin. Same thing, which in a slightly simpler format it is done. And okay, now we come to a new concept that we call as dynamic similarity. So if the power goes, there is no problem? There is no problem with this? Okay. Okay, now we come to the concept of dynamic similarity. That is, this is again about the concept of stability and when the ship becomes stable, neutrally stable, and but it's approached in a different way, that we'll see what it is. That is, okay, that is, first of all assume there is a cross section like this. Okay, now this is G, this is B0, and now the ship heels by an angle phi, and B0, this is gone to some point here, I will call it here B1, and here I draw a vertical and same way. Okay. All right. Now, draw a vertical here, and this is the meta center M. Now, look at it this way. Here we have the weight delta acting at this. I will just draw this figure, this line. Therefore, this is G and this is B0. Okay. So, at G I have a value of delta acting down, and at B0 I have a value of delta acting up. Okay. So, these two weights are acting like the two forces are acting like this. Now, what happens? It has moved into a new point, into a new shape here. Now, suppose I do this with M as center. Okay, I take this GM as the distance and I draw an arc like this. So, this will be the point of G. Okay. Note that GM hasn't changed, G is not changed because the weights have not been moved or shifted. So, G hasn't changed. Now, if you take this B0, means I am taking this B0 M initially and I am moving this distance and I am drawing an arc in the same fashion as I drew this. Okay. This in the new line B0 will be here. Okay. And this is B1, actually the new position of your center of buoyancy. Is it clear between these what I have drawn here? All I have done is I have taken the distance B0 M, and with M as the center I have drawn an arc with B0 M as the radius and B0 touching here. So, B0 will be here, B1 is here. Now, what do we see? So, this here we have B0, here we have B1, and here you have G. Now, let us suppose that the initial distance between G and B is D0. Okay, and this distance is therefore D0, this distance, right. Now, what has happened? Because of the healing, the center of buoyancy has shifted to this point B1. In this book they have written, actually it's they have taken it as bold D0. It looks, I cannot do it this, I will call this D1. Okay. So, this distance is D1 between G and the new position. Between G and the new position of B, the distance is D1 now. All right. Now, what has happened? A force delta which acted at B0 has now moved from this position to this position. It has moved by a distance of D0 D1 minus D0. Okay. Yeah. So, D1 will be greater than D0, and D1 minus D0, a weight delta has moved, right. The weight delta has moved at distance D1 minus D0. What is the work done in moving this? A force into work done in moving it is force into distance moved. Fx is the work done, you know that work done is equal to F into the distance through which it moves, F dx, dw is equal to F dx. Okay. This is the concept of work done. Therefore, because of this movement in the distance between, because of this movement in the center of buoyancy, work equal to delta into D1 minus D0 has been performed, right. That means, because of this healing, that is the final conclusion. Because of the healing of the ship, a work equal to delta into D0 minus D1 has been, D1 minus D0 has been performed. Okay. That much work is performed, and that work, the work done is known as dynamical stability. So, dynamical stability is equal to work done, or it is the energy required. You can say that it is the energy required to heal the ship. Okay. It is the amount of work done. So, you can say that is the amount of energy required to heal the ship. So, that energy or the work done amount of work done is known as dynamical stability. So, dynamical stability, and you can call it a dynamical stability arm, that is not done so much. It is, but the thing is, dynamical stability is a word used to represent the work done to heal the ship, that is dynamical stability. Now, if this is clear, we will do little bit of derivation. Now, suppose that the ship heels through an angle phi or theta. Let us do, okay, phi itself is good. So, if the ship heels through an angle phi, it heels a little bit. Now, we assume one additional thing, it heels by a small additional amount further by d phi. Initially it is heeled at an angle phi, and now it heels by an amount. So, this is the initial position. Actually, this can only be seen in figures in these. So, it is initially heeled by an angle phi. This is the initial upright position. You have G here, and you have B 0 here. Then, so note that we are doing like this. This is your position of B 0 in the new curve. This is your B 1. Then this is G in the new curve. Now, it heels by an angle additional amount d phi. Now, because of the initial amount, this is d phi. Now, because of the initial amount of heeling, that is by a heeling of phi, there is a writing arm produced. The writing arm produced is defined as the, if you remember, I did in the last class, writing arm is defined as the vertical distance between G to the new line from the center of buoyancy, means from G to this Z, G to this, from G, if I draw a vertical to this line, that will give me Z here, and the GZ is called the writing arm. Now, the question is how to draw the okay, let me draw it like this. Let us suppose this is the vertical, okay, this is 90 degrees. So, this is, I call it GZ theta, okay, means, or phi, GZ phi, not theta. GZ phi means it is the GZ when the angle of heeling is phi. Is that figure till now clear? I will complete and maybe explain further. So, this is GZ phi. Now, it has heeled by a further, heeled by a further amount of d phi, as a result of which there is again a GZ, new GZ produced, means, or rather the GZ value will change because of this new heeling by an angle d phi. Now, there will be a new GZ. The position of the new GZ, how will you get? By drawing a vertical from here to this line. Okay. Now, it will come like this, something like this. Okay. This is 90 degrees. You draw a vertical from here to here. So, this is G, this will give you GZ phi plus d phi. Phi plus d phi is a subscript, it is not a value or anything. So, GZ when the phi, when the heel is phi plus d phi, that is GZ of phi plus d phi, the other one is GZ of phi. So, you get two GZs, GZ at phi, and you get a GZ at phi plus d phi. Okay. Now, let me draw this part alone. So, you have G and you have you will have Z theta Z phi, and you will have this will be Z. I will explain this again if it is confusing, phi plus d phi. So, okay, I am just drawing this figure part. This GZ line is just GZ, this GZ plus phi I am drawing it here, it will be like this. Now, note that here you have phi, if this is the point, here you have a phi, and here you have phi plus d phi. So, two lines like this. Now, if you see that, if you see the geometry, you will see that this angle becomes d phi, because it will be like this. Actually, this is not parallel to this one, it will be like this. Okay. Okay. Now, if this is d phi, the figure is not correct, that is why you are not able to see it, but if this angle is, if this is phi and that is d phi, this angle will be equal to d phi. Just do it, because these angles are 90 degrees, it is not very difficult to derive this. Okay. Now, if that is true, what is this distance, the vertical distance between this point and this point, which is your d1 minus d0, the vertical, that is the difference between, note one more thing, this represents a vertical line, means when a ship is there and heeled, what do? We draw a water line through this, that water line is horizontal, okay, though the curve it looks inclined, it is actually horizontal, like that this line and the perpendicular to that water line, which is the line through the B, will always be a vertical line. So, just like this is a vertical line. So, this distance between this point and this point, this distance will give you actually d1 minus d0. So, d1 minus d0 will give you, this will be given by this value, which will be now gz, I think it is dz tan d phi, okay, which is equal to g, which can be written as gz d phi, okay. This is actually d of this, because this is there is a d phi on this side, it is d of on the other side also, otherwise it does not make sense, right. I will explain this again, I can see everybody is confused. So, anyway, then once you have this, then you will have d1 minus d0 will be equal to integral of gz d phi. I am just using this, d of d1 minus d0 is equal to gz d phi. So, integral of d1 minus d0 is equal to d1 minus, integral of d of d1 minus d0 is d1 minus d0 is equal to integral of gz d phi. So, this is the expression that I want to derive, I will explain it again. So, this is the, what does this represent, gz d phi, integral gz d phi, it actually represents the area under the gz phi curve. Integral g, what is gz phi curve again, it is called the curve of statical stability. So, the area under the statical stability curve is what you are calling as dynamical stability. Area up to a particular phi, it is like this, means if it is heeled between 0 and phi, you will get the area, if you take the area from 0 to phi in that curve, statical stability curve for that ship, you will get the dynamical stability or the work done that is required in heeling the ship from phi equal to 0 to that phi. Again I will repeat, dynamical stability is the work done, or it is the amount of energy to be expended to to heel a ship from phi equal to phi 1 to a phi equal to phi 2, means if it has to heel through a small angle phi, that heeling is given by, that amount of work done is given by dynamical stability, that is the meaning of it, and it is given by this d1 minus d0, okay. And it is the area is, you have seen it is equal to gz d phi. Now, I mean this is d1 minus d0 is the dynamical stability arm, and delta into d1 minus d0 will give you the dynamical stability. This is the real meaning of dynamic, this is a meter, right, d1 minus d0 is meter, means it is a unit of distance. So, it is a dynamical stability arm, and delta into d1 minus d0 will give you the energy or work done, it is given by, this is really what you mean by dynamical stability, and therefore, the area under the gz will give you the dynamical stability arm. And so, whenever you are talking about dynamical stability, note that someone asks you what is dynamical stability, you can very simply say that it is the area under the gz curve, gz phi curve, or it is the area under the statical stability curve, that is the meaning of dynamical stability. But what does it really represent? It represents the amount of energy required to heel the ship, and it is equal to the area under the gz curve, it is equal to integral of gz d phi into delta, of course. So, delta into area under the gz phi curve will give you the dynamical stability. What is the advantage of dynamical stability? Now, you can see that we are now looking at stability from a slightly different point of view. Last time, previously what did we have? We had a heeling moment which produced a ship to heel by, in that initial derivations we did not really look at how the ship healed, rather we were looking at the final it is healed by some due to some reason and uniformly healed, that is another thing. We are assuming it uniformly healed and it came and rested there, how it goes back to its initial position, very uniform conditions. Now that is not how it is in real practice, means in real practice what will happen is that for 10 minutes for instance very strong wind might blow, it is like an, the word is impulse, I think it means a sudden impulse is provided. So it is not a uniform force acting, means it is not like uniformly going like this, that concept does not hold really. If it is, if you assume that, then all our work is okay, but if there is a sudden wind blowing for a 10 minutes it blows very strongly, then it stops, after 10 minutes it blows again, like that, it is like impulsive, means it is like intermittent very strong forces acting, not a uniform force but very strong forces acting in very short times. Therefore we cannot really study in a steady fashion the whole thing, you have to, the only way you can study it is by using the energy. What you say is that the amount of energy provided by the wind is equal to the amount of energy going to heal the ship, and from that you can find phi in this case. That means that much of healing you can study, that much of healing is produced due to that wind that has come, that is due to that wind that acted for 10 minutes, how much energy has come in, that much energy has gone to heal the ship, and from that you can get phi, that much of healing is required. The other study assumed a uniform force is acting, so uniformly it's continuously uniform force is acting, so it continuously moves like this, it goes up to phi, so we can calculate what is the phi produced due to a force and all that. But since it is not true, this dynamical stability becomes a much more powerful tool to study this kind of the real cases. That is why the concept of dynamical stability came. Now I will just explain this again, okay. Now okay, I will start from this thing again. This I think is clear, that is d1 minus d0 from this figure I think is clear. So delta into d1 minus d0 is your dynamical stability, that is clear. Now once you have that, suppose you have a ship in its I am just repeating it, in its initial position like this. Now this is what I have represented by this line, okay, the initial position of the vertical, and the water line is somewhere horizontal, okay. So this is G, this is B0. Now it is healed due to some factor by an angle phi, so this is its new position. Note that this is also vertical, from geometry you do not have to think of all that, but in real practice it is a vertical, because a horizontal water line is like this, but let us forget that. So this is phi, it is healed through an angle phi. So here you have, I have already explained to you that what is known as the writing arm GZ is a vertical that is drawn from G to this line, to the new position of B, to the new position of B, if you draw, means to the new line through B, if you draw a vertical and then the that line hits there at Z, and that distance is called as GZ. So this is GZ phi, or it just means that when the healing is phi, the Z produced, the Z at that point is called Z phi, and that distance is GZ phi, okay. Now it is healed further by a small angle d phi, this small angle d phi. So it is healed further and it is here, this is the new line, okay. Now again note that this is also vertical, we are talking only, so when you are measuring distance like this it is also vertical, when you are measuring distance that is also vertical, that is also vertical. Now similar to what it is at G, like a GZ you have GZ phi you have already done, you do a GZ phi plus d phi, same thing, means what has happened at phi you do it continue, you repeat it for phi plus d phi. So here you have another G Z phi plus d phi, okay. So I have drawn this line G Z plus phi, d phi. Now if you just take that small part out, this will look something like this, there will be a G Z phi like this, G Z d Z plus Z phi plus d phi like this here, so two of them, and this angle will be d phi. Now this distance will be d0 minus d1, d0, what is d0, it is again what is d0, this is b0, this is b1, okay. Now if, okay, that is probably an assumption that, but that is straight away, means if this is if this goes through as means what is this distance is d0, it G comes here somewhere, this distance is d0, it moves by a distance slightly moved distance d1 minus d0, z moves by a same distance z1 minus z d1 minus d0 again. So, this distance will give you d1 minus d0. This distance is equal to gz tan phi, which can be written as gz d phi, it's dz tan phi, which is dz phi. Okay. Basically gz phi, let us remove the d phi and all that. Okay. So, you get so from that you get this expression that d0 minus d1 is equal to integral of gz d phi, which implies that d1 minus d0, which is the delta into d1 minus d0, which is known as the dynamical stability, is delta times the area under the gz curve, and area under the gz curve is the dynamical stability arm, and delta into gz under the delta into area under the gz curve is the dynamical stability, and that is known as the work done to move the ship, heal the ship, that is dynamical stability. Now, okay, now we will just mention, this is actually an important concept, means later in the later part of the course you will see some rules which are usually the IMO rules, International Maritime Organization. So, they have their own rules regarding how the, I mean they have to, they have specified a set of rules which tell you whether the ship is safe or not, or the ship is and based on that rules there are some, means every ship has to get a certificate from a, I have already told you, every ship before it is put in practice has to get a certificate from a organization, something like the Lloyd's Register, or like in India we have the Indian Register of Shipping, all these IRS, Lloyd's Register, or American Bureau of Shipping, all these different shipping agencies are there for different countries, from them they have to get a certificate. So, the rule that the that organization like the Indian Register of Shipping looks at is made by the IMO, called the International Maritime Organization. Now, one of the rules is like this, it is not just the IMO, now there is a something known as, okay, this is just for merchant ships, merchant shipping, it is called load line rules. Anyway, there are different types of rules made by different of course people do research in universities only, and other basins they come up with the rules, they modify the rules, and these organizations adopt those rules and they give the certificate. So, one of the some of the rules we will look at which are very important, one of them is that the area under the GZ curve for any ship, area under the GZ curve means GZ curve is always with respect to phi, okay, the other coordinate is always phi, so it is GZ phi, that is the statical, so we call that GZ curve. GZ curve is always this curve of GZ versus phi, so that nobody mentions phi, GZ phi curve or anything, it is called the GZ curve. So, the area under the GZ curve should be greater than, okay, it should be greater than 0.055 meter radians up to an angle of 30 degrees. Means if you take, let us suppose this is your GZ curve. Now, if this is obviously about 57 degrees, 57.3 degrees. Now, if this is 30 degrees, the area under this curve up to 30 degrees, whatever be the ship, whatever be the type of ship and anything, this is fixed 30 degrees, up to 30 degrees your area should be greater than or equal to 0.055 meter radians. I think you should just by heart these numbers, there is nothing else to do here. So, 0.055 meter radians up to an angle of 30 degrees, then it should be greater than Now, the GZ curve that is up to 30 degrees. Now, this is now it also says that this GZ curve should be greater than or equal to 0.09 meter radians up to 40 degrees, or suppose that before that 40 degrees some opening is there, means in the ship's hull there actually on the hull there is a water line, most likely there is be no openings below the water line, okay, it will be closed everywhere, but above the water line in general after some height there will be some openings here and there to do ballast sometimes, to put the anchor sometimes, different lot of such openings are there. Okay. Now, if in fact even air holes might be there, ventilation, different kinds of things are there. If the ship heels beyond 30 degrees, so what this says is that the ship should be designed always such that when it heels up to 30 degrees there should be no such hole that is going under the water. Every ship is designed like that. So, up to an angle of heel of 30 degrees no hole will go under. So, that is fixed. After 30 degrees there are some ships where holes can come. Now, when that happens up to that angle, or if there is no hole up to 40 degrees, your this area under the GZ curve should be 0.09 meter radians. That is the second rule. These two rules are to be very strongly followed. And in addition, now there should be between 30 and 40, this is the third rule, between the 30 and 40 radians degrees, between the 30 and 40 degrees there should be at least 0.03 meter radians of area. It does not have to be 40 degrees, if it is also a hole coming before that, that is up to that degree, there should be a 0.03 meter radians of area in this GZ curve. So, that is, these are three important rules. So, these are rules. So, this is how rules are made in the basis of dynamical similarity. These three things relate to dynamical stability. These are rules associated with dynamical stability. And there is a parallel set of rules regarding GZ also, that also you have to know. So, this is one set of rules that should be followed strictly. So, when they are means they will measure the area and means they will draw the GZ. So, it is important that for a ship you should be able to draw the GZ curve. So, once the ship is made and it is given to that organization, they will draw the GZ curve and they will measure the areas and make sure this happens, this is satisfied. Now, a couple of other rules are also there that needs to be satisfied, that is that the GZ not less than, sorry, greater than or equal to. Note that we have the curve of GZ. I have drawn it here. So, it comes like this. Now, let us suppose this is 30 degrees. So, whatever be the ship, it means that at 30 degrees at an angle, this should at least be 0.2 meters GZ. This is a strong criterion for the stability, that is GZ should be greater than 0.2 meter. Then and number 2 is we have already drawn the GZ curve, okay, and we have seen that GZ reaches a maximum value and then starts decreasing. Now, another rule says that this maximum GZ should never occur before 30 degrees, okay, for a ship. So, the GZ should always occur after 30 degrees for a ship, somewhere anything after 30 degrees is acceptable. So, the value of maximum GZ should occur only after 30 degrees. Then then another rule is that we have already said that we have already derived that the condition for stability is that GM should be greater than or equal to, or is it greater than or equal, greater than 0, right? That is the condition for stability. So, but in practice we do not say that GM greater than 0 is the criterion, we say that GM should be at least 0.15 meter, okay. That much of clearance is given for different purposes of the ship. So, that GM transverse should be greater than at least it should at least be equal to 0.15 meter. So, these are some rules that are to, so these are rules related to the dynamical stability, related to GZ and related to GM. So, 3 set of rules that are important. So, as I said, you have to really by heart these numbers 0.2 and 0.15, 0.03 and all that you have to remember. Yeah.
Sir, in rule number 2, what will happen if GZ occurs before 30 degrees?
Actually, the exact other conditions, what will happen, it means that it will be unstable. Now, why should it be unstable is your question.
Actually, stability will increase now, sir. When GZ comes before 30 degrees, that means the area under the curve is increasing. That means for more energy, it is having a lesser heat.
Means more energy, it's having a lesser heel. That makes sense, but let me see.
That's the basis for all the other rules.
Which one is it? GZ, maximum GZ. Actually, I need to think about this. I will tell you. That is a good question. GZ, but the rule says that. So obviously, there is some other criterion that I will tell you that. I have to.
Phi ultimate will be small if.
Which one? Phi LT. What is Phi LT? Huh? Oh, vanishing stability. GZ becomes 0 at that point. Okay. If that is, if it goes here, then GZ might be that is less. That could be a reason. You see, understand what he said now? He says that if the curve shifts like this, the vanishing stability might happen at a smaller angle. If it goes like this and crosses here, the vanishing stability comes here, right? So that might be a reason. That is a good possibility, but I have to really see what it is. Actually, that seems a good reason. I'll tell you. Okay, then so these are some rules, and from this you have now we can have, there can be some ships designed, you will have end up with some different kind of curves, like what will happen if you have a GZ curve like this. Okay. This is a slightly different form. This is GZ versus phi. What it means is that, what does it mean if, okay, let us see that. If the curve is going down, what does it mean? It means that GZ is negative, obviously, and that means writing arm is negative. What does it mean? Writing arm is negative. It is trying to heel it, actually, it is trying to capsize, it is not writing it, it is going the other way around. So at this point, any of these regions where GZ is negative, okay, the ship is initially upright. Now some small factor, let us say a wind came, it heeled like this. Now what will happen? The writing moment itself is going to cause it to heel. So it will continue to heel and till it reaches here. At that point, when it reaches there, any more heeling, the writing moment is positive after that. So after that it will tend to come back. Now the ship will remain like this always. So the ship will be going like this always. Okay, this, the ship will be like this. That is a end result of such a GZ curve. It is of course stable, but it is a strange kind of step in, that is, it is unstable in the region before this. From this region to this region it is unstable, but beyond that it is stable. So this is known as lol, and that angle is called the angle of lol. and the phenomenon itself is called. So, the if you are told that ship is lol or ship is angle 10 degrees. So, if you are told that the ship is lolling at an angle of 10 degrees, obviously you can draw your GZ curve like this. This is the meaning of your GZ curve. Okay. So, that means at an angle of 10 degrees only it seems to be stable. Beyond 10 degrees it will come back to its position, because the GZ curve is writing arm is positive, but before that the writing arm is negative. So, it causes it to heel, it causes it to move in this direction, causes it to remain at 10 degrees. So, this is an angle of heel, this represents a ship going like this. Again, this is a common question for your Viva and interviews and all, they ask this. They say either the other way or this way, means they will draw a GZ curve like this, they will ask you what does this mean, what does this imply about the ship, or you are asked if the ship is going like this. Let us suppose that the ship is going with an angle of lol, draw the GZ curve. Two, okay, from there or from here, two ways. In any case, this you have to know, if you understand why it is so, it is very easy to remember. This is all there is to know. That is, in this region, from here onwards your GZ is positive, that means your writing arm is positive. It means that anything causing it to tilt further, the writing arm will be positive, causing it to come back. So, there is no problem as far as this region is concerned, but here in this angle, means when it is between 0 and 10 degrees, between that angle of heel, if it heels by some factor, let us say wind caused it to slightly heel, the writing arm will itself cause it to heel in the other direction, and will cause like this, and it will go till it is 10 degrees. Beyond that the writing moment will try to bring it back. So, the ship will remain at this. So, in general the ship will be going like this. Okay. So, if it heels more than the lol angle, it will come back to the lol angle. So, it will be like this. If it is like this also, it will be pushed back here. If it is like this also, it will be pushed back here, and finally it will go like this, most likely. I mean, slight variation, it means a ship is like this, it never goes like this, it always goes like this. Okay, right, means a ship will ever be upright when it is, even if it is a good ship, it will never remain upright, it will always heel a little here and there. That is why we are doing all these calculations, but the other ship, this ship will be in this position, it will heel like this. Okay, means its general mean motion is like this, that is the meaning. That is called lolling, that angle of lol it is called. So, there is a unstable equilibrium, between this angle of 0 and phi of lol, the angle of lol. And therefore, this is known as, so between phi equal to 0 and phi equal to the angle of lol, the ship will be in unstable equilibrium. Okay. So, I think I will stop here. Thank you.